Let's talk about one more piece of technology built on top of Spark Core, GraphX. Pretty powerful thing. Now, we're not talking about graphs in the sense of, charts and lines and stuff like that. These are graphs in the computer science sense. Things like social networks. So if you think back to the example we did of a superhero social network, we're going to come back to that throughout this lecture. That's an example of the graph we're talking about. It consists of vertices, where each vertex in this case would consist of an individual superhero. And there are many superheroes in this graph connected by edges that represent relationships between given superheroes that appeared together in the same comic books. Now, GraphX is mostly useful for giving you sort of high-level information about a graph. So for a social network, it can tell you things like how many triangles appear in the graph in connections, how connected is the graph as a whole, what are the degree distributions, the average path length, things like that. It also has some very highly specialized functions in it for doing things like applying the PageRank algorithm to a graph. And it can join different graphs together quickly and apply transformations to an entire graph all at once. Mostly it gives you a way of actually representing a graph in a structured way, where we have a graph object that consists of vertex RDD specifically, and edge RDDs that connect these vertices together. So for things that are more specialized, like what we did with computing the degrees of separation between superheroes, it's not going to give you a function to just do that. You have to do that kind of the hard way. But it provides a framework that lets you do those sorts of operations a little bit more simply than the way we did it before, and that's called Pregel. We'll talk about that more in a little bit, but it's basically an algorithm that you can apply to a graph that defines how you iterate through it and branch out as you explore a graph in any way that you want to. So like I said, it introduces a couple of new data types, the vertex RDD, the edge RDD, and a vertex and an edge. So vertex, again, just an individual node in your graph. Edge is a connection between two nodes, and a graph is constructed by passing in an RDD of vertices and an RDD of edges that connect these vertices together. So an edge just consists of two vertex IDs that an edge connects, and a vertex is just a vertex ID and whatever data you want to associate with that vertex. Apart from that, there's nothing really special from a syntactical standpoint. In fact, when you're creating a vertex RDD, you're not really seeing a whole lot of GraphX-specific stuff here at all. The only thing that stands out here is the vertex ID type here. So what we're going to pass into FlatMap as we're creating our vertex RDD from the source data is a tuple of vertex IDs and strings, which in this case is just mapping superhero IDs to their names. So this is an example of where we're actually going to go through the marvel names.txt file and create a list of vertices from every superhero in that file. So all we do is split it up, extract the superhero ID, and that will be our vertex ID. A little example here of cleaning the data, which is always important. We happen to know that everything above 6486 are actually bogus characters in that data file. They don't show up in the data at all, so we're just going to discard them. But if the superhero ID is valid, we will return the superhero ID converted to a long, which is the same thing as a vertex ID, and the superhero name. So this is returning a sum instance that indicates that we actually have a result of the superhero ID converted to a vertex ID and the superhero name. And if it is an invalid entry, we return none, and FlatMap will just ignore that entry. Now for making the edges, not much more complicated here. In this case, we're going to go through the actual Marvel data here for the actual connections. And if you remember, each line of input here is the superhero ID followed by a list of the superhero IDs of all their connections. So what we return here is actually a list of edge objects, and these edges are wrapping integer types that are just the superhero IDs themselves. So given a line of input, we create a list buffer so we can build up multiple edges, because we're going to end up with an edge for every single connection between that ID and every character that they appeared with, right? We split it up, extract the hero ID that we're talking about, and then we create a new edge for every connection in that line of input. So the new edge is created with the hero ID in the first position, and then with every subsequent hero ID that they are connected with. We build up that list buffer, convert it to a list, and return it back to FlatMap, and we end up with a edge RDD in the end. Putting it all together, load up our marvelnames.txt file, call FlatMap with parse names, so we get back our vertex RDD that contains all the superheroes that we know about. We will then load up the social graph itself and construct edges based on that information. So now we have an edge RDD. And to create our graph, all we need to do is call graph with a vertex RDD, an edge RDD, a default case for in the instance where we have an edge that points to an undefined vertex. So in that case, we'll just call that hero nobody. And we're going to cache that because we're going to do a bunch of stuff with it. So that's all there is to actually creating a graph in GraphX. So once we have that graph constructed, we can do cool stuff with it. So for example, let's say we want to find the top 10 most connected superheroes. That's actually pretty easy to do. You can just call graph.degrees, and that will give you back a vertex RDD that contains all of the degrees of connectedness. Okay, so all the actual, how many lines are actually emanating from every individual vertex. And we might want to join that back with the vertices themselves so we can actually print out their names. And then it's just a matter of sorting them, taking the top 10 and printing them out. So that's an actual line of code that would print out the top 10 most connected superheroes given that graph that we just created. Pretty cool stuff. One line of code, that's all it takes. But what about doing breadth first search? So at this point, you might want to go back and rewatch that lecture about doing breadth first search using Spark the hard way. It goes through the algorithm a little bit more deeply. But if you remember, ultimately we're iterating through this graph from some given starting point. So let's say we wanted to measure the degrees of separation from Spider-Man to some other superhero. We're going to start with Spider-Man and iterate through that graph, expanding it out one step at a time until we find the person we're looking for, and we'll keep track of how many steps it took to get there over time. Now with Pregel, that gives us a general algorithm for actually doing iterations through a graph in a general manner. And we can actually implement breadth first search using the Pregel algorithm in a little bit more of a simple way than we did before. So let's take a look at how that works. So Pregel is just a general purpose mechanism for walking through a graph and doing stuff as you go. So it's very extensible into different problems. At a high level, the way it works is every vertex sends a message to other vertices, their neighbors, the ones that they're connected to through edges. And this happens in iterations that are called supersteps in Pregel. And through each superstep, the following three things can happen. Messages from the previous iteration are received by each vertex. Each vertex can then run a program to transform itself, and then each vertex can send messages to other vertices for the next stage, for the next superstep. Okay, so basically, a superstep consists of receiving messages from other vertices, doing some sort of processing on the vertex, and then sending out messages to new vertices. And it does this over and over and over again until you say you're done. So how do we apply this to breadth first search? Well, first we create our initial state. So given that graph, what we're going to do is call map vertices on it. And this is another GraphX function that lets you transform an entire graph at once. And all we're going to do is say, for a given ID, if it's equal to the root, Spider-Man, say, the person we're trying to measure degrees of connection from, we will set the property of that vertex, the value, to 0. Otherwise, we'll set it to positive infinity. So this is the initial state, if you recall. We start off with the person that we're starting from with a distance of 0, while everyone else has a distance of infinity. And then we can kick off Pregel to actually do the iterations. So what do we do at each stage? Well, first thing we do is we have to figure out what messages we're going to send from each vertex. So this is the function that actually sends the messages off. And what it does is it says, well, as long as I have an actual value, I'm going to go and call all my neighbors with that value plus 1. Otherwise, I'll do nothing. So in the case where I have a white node that still has an infinite distance, we're going to ignore those ones. But if I have a value that I haven't dealt with yet, I haven't actually walked to this point yet, what I'm going to do, increment that attribute by 1 and send that to the neighbors. Okay, so we're doing the same thing that we did before, just using the Pregel construct. We also need to preserve the minimum distance as we go. So if you recall, there's often multiple ways to get to a given node, and we want to make sure that we're preserving the shortest path. And in this example, we're doing that in 2 ways. The vertex program is actually making sure that if we receive a message and we already have a distance in our node, we're going to preserve the minimum attribute, the minimum distance. Okay, so if someone's trying to send me a distance and I already have a distance that's lower than that, I'm going to keep the lower one. And also, we have a reduce operation that we specify in Pregel for the case of multiple things hitting a node at once. And in that case, we will specify a reduce operation that says we want to preserve the minimum distance being sent to me in the event that I have more than one. So how does that actually look in code? Well, it looks like this. Pretty simple. So we have that initial state where we set up everything with an initial value of positive infinity for the distance and 0 for the one we're starting with. We say here that we're going to take the minimum of the distances that are sent to us. Our function here will send off messages to our neighbors with the distance incremented by 1. And if we receive more than one message at once, we will preserve the minimum one. Okay, so that's it. All you do is call Pregel on the graph itself. And these parameters mean this is the initial message being sent to positive infinity, the maximum number of iterations I want to run, so we'll give up after 10 iterations. And we just pass it in 3 functions that are the reduce operation, what we do when we receive a message, and how we actually send off messages to other vertices each step. So that will automatically do the iteration for us, and that actually implements breadth first search in a much more compact way than we did before. So let's do it. Let's actually see if it works.